Welcome to Selection with Sathi. Today we learn union find, also called disjoint set union or DSU. This data structure efficiently tracks which elements belong to which set, supports merging sets, and answers connectivity queries in nearly constant time. It is a must-know for gate CSE, placements, and coding interviews. Let us begin. Let us start with the find operation. Look at the code on the left. Line 1, find takes the parent array and element x. Line 2, if x is not its own parent, it is not the root. Line 3, this is path compression. We recursively find the root and set parent of x directly to the root. This flattens the tree so future finds are nearly O of 1. Line 4, return the root. Without path compression, find can be O of n in the worst case. With it, the amortized cost drops to O of alpha n, where alpha is the inverse Ackermann function, which is practically constant. Now the union operation with rank optimization. Look at line 2, first find the roots of both elements. Line 3, if both have the same root, they are already in the same set. Return false. Lines 5 through 8, attach the shorter tree under the taller tree. This keeps the overall height small. Lines 9 through 11, if both trees have equal rank, pick one as root and increment its rank by 1. Union by rank ensures the tree height never exceeds O of log n. Combined with path compression, this gives the optimal nearly O of 1 amortized time. Initialization is straightforward. Look at line 2, parent of I equals I for every node. This means each node is its own root, forming n singleton sets. Line 3, all ranks start at 0. Look at the example below. For 5 nodes, parent is 0, 1, 2, 3, 4 and rank is all zeros. Each element is in its own separate set. As we perform unions, sets merge and parent pointers change. Initialization takes O of n time. A classic application, counting connected components. Look at line 2, initialize DSU for n nodes. Lines 3 and 4, for each edge, union the two endpoints. After processing all edges, nodes in the same component share the same root. Lines 5 through 7, find the root of every node and collect unique roots. The number of unique roots equals the number of connected components. This runs in O of E times alpha n, which is practically O of E, much simpler than running BFS or DFS from every unvisited node.
Let us trace union find on 6 nodes. Initially, each node is its own set. Union 0 and 1, both are roots with rank 0. Make 0 the root, rank of 0 becomes 1. Parent array, 0 is parent of 1. Union 2 and 3, same situation. Make to the root, rank of 2 becomes 1. Union 0 and 2, find root of 0 is 0, find root of 2 is 2. Both have rank 1. Make 0 the root, rank of 0 becomes 2. Now 0, 1, 2, 3 are all in one set. Union 4 and 5, make 4 the root. Final, to components. Component 1 has root 0 with nodes 0, 1, 2, 3. Component 2 has root 4 with nodes 4, 5. Now let us detect a cycle. Graph has edges 0 to 1, 1 to 2, and 2 to 0. Process edge 0 to 1, find 0 gives root 0, find 1 gives root 1. Different roots, so union them. Process edge 1 to 2, find 1 gives root 0 now, find 2 gives root 2. Different roots, union them. Process edge to 0, find 2 gives root 0, find 0 gives root 0. Same root. Both endpoints are already in the same set. Adding this edge would create a cycle. This is the key insight. If find of u equals find of v before union, the edge uv creates a cycle. This technique is used in Kruskal's algorithm to avoid cycles in the MST. Let us count connected components in a graph with 8 nodes. Edges 0 to 1, 1 to 2, 3 to 4, 5 to 6, 6 to 7. After union 0 to 1, nodes 0 and 1 merge. After union 1 to 2, node 2 joins the set of 0 and 1. After union 3 to 4, nodes 3 and 4 form their own component. After union 5 to 6 and 6 to 7, nodes 5, 6, 7 merge into one component. Now find root of every node. Nodes 0, 1, 2 all have root 0. Nodes 3, 4 have root 3. Nodes 5, 6, 7 have root 5. 3 unique roots means 3 connected components. Finally, Kruskal's MST using union find. Sort edges by weight, 0 to 1 weight 1, 1 to 2 weight 2, 0 to 2 weight 3, to 2 3 weight 4, 3 to 4 weight 5, 1 to 4 weight 6. Process edge 0 to 1 weight 1, different sets, add to MST. Cost is 1. Process edge 1 to 2 weight 2, different sets, add. Cost is 3. Process edge 0 to 2 weight 3, find 0 and find to give the same root. Skip. This would create a cycle. Process edge to 2 3 weight 4, different sets, add. Cost is 7. Process edge 3 to 4 weight 5, different sets, add. Cost is 12. We have 4 edges for 5 nodes. MST is complete. Total cost is 12. Union find made cycle detection O of alpha n per edge.
Quick exam tips. First, with both path compression and union by rank, the amortized time per operation is O of alpha n, which is inverse Ackermann. For all practical purposes, this is constant. Second, union by rank and union by size give the same asymptotic bound. Rank tracks tree height, size tracks element count. Either works. Third, path compression halving is an iterative alternative. In a loop, set parent of X to grandparent. Same amortized complexity. Fourth, Gate loves DSU for cycle detection in undirected graphs and as a subroutine in Kruskal's MST. Practice both patterns. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.